I think screen is coming to you. Okay.
Yes, sir.
Yes. Last week, the first week, we had a discussion on poly generation, introduction, and the elements of poly generation. And my voice is audible to all of you. Is it clear?
Yes, sir.
Okay. And now the element by element, I am going to explain for the poly generation development. Finally, the one of the important element in poly generation is the cooling system. Apart from the power and processing, poly generation is one of the important element, subsystem. I am saying. So this subsystem can be used in two ways. One is for cooling purpose, what we are calling as vapor absorption refrigeration system here, or it also can be used as power generation element. That is called as vapor absorption power plant. That's a specific name for vapor absorption power cycle. As per the inventor, it is a Kalina cycle. Vapor absorption refrigeration cycle, there is no inventor name because that is also Rankine cycle. The Rankine cycle invented, but in the reverse direction. The reverse cycle, Rankine cycle, but exactly it is not following the Rankine cycle principle. Vapor compression refrigeration, you know, that is following the reverse Rankine cycle principle. Because each and every process is separate, there is no addition or mixing, and single fluid system. Vapor compression refrigeration is a single fluid system. Rankine cycle also single fluid system. But in vapor absorption, this is a binary fluid system. That single fluid system is modified with the binary fluid system. Vapor absorption system, it is a binary fluid system. That's why Rankine cycle is termed as a modified Rankine cycle, and reverse Rankine cycle is called as modified reverse Rankine cycle. Very specific names of this modified Rankine cycle is Kalina cycle as per the inventor for the power generation, and vapor absorption refrigeration, there is no specific scientist name. That's why still we are calling this as VR only, that is the vapor absorption refrigeration system. Apart from these two options in binary fluid, that is designed for subsystem is designed for cooling purpose, or subsystem is designed for power system. There is a third option is there, which is a wonderful option, I can say, as per my outcomes. The combined the power and cooling is also possible. What I showed in some of the examples of this poly generation, instead of installing two separate plants or subsystems like cooling separate and power separate, a single unit can be devised such that in the binary fluid system, such that the single fluid system, that's a vapor absorption system, can supply both cooling as well as the power. But before going to solve those cooling alone or power alone, or both cooling as well as the power from the combined system, we need to focus on the nature of the properties of this binary fluid system. There are many pairs are available in the literature like LIBR, the lithium bromide water mixer, aqua ammonia, that is NH3H2O mixer, KOH and NH3. There are many such options are available. Out of these options, in case of the cooling, some cooling applications like air conditioning system, generally air conditioning system no need to maintain below 0 degrees centigrade. Okay, that's it. That is always ambient. I mean, that's space temperature is maintained above atmospheric. That means above 0 degrees centigrade only. That's why instead of suggesting ammonia water mixer, the vapor absorption used for air conditioning is, as per the market survey, I'm saying, lithium bromide water mixer they are using, because that lithium bromide water mixer is suitable for above 0 degrees centigrade. Air conditioning is the best example for above 0 degrees centigrade. But some applications like cold storage, refrigeration, where we are maintaining the low temperature below 0 degrees centigrade. And below 0 degrees centigrade, if you are using lithium bromide and water, that is not suitable because water becomes the ice and blocking of the pipes, etc. It takes place. As well, lithium bromide water mixture is not suitable for a low temperature below 0 degrees centigrade. What is the alternative option? Ammonia water mixture is a best option. A best working fluid also compared to other fluids. I am saying water is the ideal fluid, in all the applications, especially for the power plant, thermal power plant. So ammonia water mixture is good for low temperature applications where we can maintain below 0 degrees centigrade, such as cold storage and refrigeration and similar applications. Okay. Now coming to this, the fundamentals, that is before going to the solutions of this number of the.
Excuse me, sir.
Yes, yes.
Sir, I think slide does not change. Only first slide is shown continuously.
Yes, yes. First slide is showing, yes, yes. I didn't change it actually. I'm giving introduction. Yes, yes. Thank you for your feedback. Actually, I'm giving introduction. It's fine. It's fine. So these are the outcomes. What I'm going to deliver through this topic is including the applications level. You can capable of solving, design binary fluid system for poly generation. Ultimately, that is the poly generation is your goal. But to solve the poly generation, you need to solve the subsystems like refrigeration system as well as the Kalina cycle, that's Weber power systems. And what I showed in last week, a book is available in our central library. I think I think in case you are coming offline time, I will share the hard copy. Unfortunately, I don't have the soft copy. This hard copy I will share to you to follow what I am teaching, the characteristics of the thermodynamic properties in the first level, and second is the process conditions. That means various process involved in cooling purpose as well as the power purpose. After finishing the property level and process level, then directly we can jump into this the plant level, the system level. I can say the system level. Yeah, actually this book is dealing the systems, all the systems. I can say that's why the title of the book is a flexible Kalina cycle system. The meaning of this flexible is it has the flexible to develop to design, evaluate the cooling systems alone and power systems alone, combined cooling as well as the power system. So one subsystem entirely, completely, this book is covering the complete subsystem which we can adopt into the poly generation. But the poly generation book, that is coming in the in 2022 only, next year only. This year I can share only this one, that is a binary fluid system. Are you able to see the blackboard?
Yes, sir.
Yes, sir.
In binary fluid system, first I want to show the regions in the fluid. Let us say the A plus B. There are two fluids. One is A and second is B. A has certain advantages and disadvantages. B has certain advantages and disadvantages, because we can't define a single fluid which is satisfying all the expectations. Of course, water is meeting more expectations, but still it has certain limitations, like we can't use the water for low temperature applications. Let us say you have a source at 100 degrees centigrade or 150 degrees centigrade, between 100 and 150 degrees centigrade. Using water alone, we can't generate the power, because that steam generation and pressurized high pressure steam, it needs high temperature source, maybe 500, 600, but not 100 degrees centigrade. At the same time, you can't generate the cooling system using water alone. That's why what we are doing, we are mixing another fluid. Let us say here NH3. NH3 is capable of producing low temperature, that is below 0 degrees centigrade, and the NH3 alone, if you are using for cooling or for power, NH3 cycle means that we can say organic Rankine cycle. Only NH3 I am saying. What is the limitation? Why we can't generate the power as well as cooling? Yes, we can generate, but difficulties are there. At sink temperature, we have to maintain very low temperature. Even sometimes it needs close to 0 degrees centigrade. We need to reject the heat. Cooling system, we have to reject the heat. That's absorber or condenser, whatever it may be. Similarly, the organic Rankine cycle is also, we have to reject the heat in the condenser, maybe air-cooled condenser or water-cooled condenser. That means the difficulty in NH3 based power plant or NH3 based cooling plant is the low temperature heat rejection. Or you may say, yes, you may design a condenser at, let us say, 30 degrees centigrade, and you may select the properties of NH3 accordingly. Yes, that is possible, but very high pressure you have to maintain. NH3 alone, let us say if you want to reject the heat at, let it 30 degrees centigrade, NH3 alone, maybe power or cooling, nearly 8 to 10 bar pressure you have to maintain. At the sink, I am saying, not at the source. At the sink itself, you have to maintain that much amount of pressure. That is also difficult. Maintaining high pressure is difficult. Or maintaining very low temperature for the heat rejection, that is also difficult. That's why we are taking the help of another fluid. We are taking the help of another fluid. What it is contributing? H2O. Even though H2O alone is now we can't use for cooling generation or power generation, but it is supporting the NH3. How it is supporting the NH3? One is the temperature, boiling point. At atmospheric temperature, the boiling point of NH3 may know approximately from you. The boiling point of NH3 at atmospheric temperature. Exactly not necessary, I am saying approximately. At the BTech, you studied these mixer properties, that's why I am asking. If you don't know, leave it out. How much?
So that is about minus 40 degrees Celsius.
Hello?
Minus 40, sir.
Minus 40. Yes. It's approximately close to minus 35 degrees centigrade. So minus 35 degrees centigrade, is it possible to, at atmospheric pressure, the boiling point is minus 35 degrees centigrade. Just I rounded nearest number, minus 35 degrees centigrade. Would you see the liquid? For example, in condenser means we have to condense the NH3 vapor completely into the saturated liquid condition. Can you see the NH3 at atmospheric conditions in the liquid form? Nobody can see. Why nobody can see NH3 at atmospheric conditions, liquid NH3 at atmospheric conditions? Because the boiling point itself is minus 35 degrees centigrade. Once you are seeing the atmospheric conditions, the temperature of atmosphere, let us say, is 30 degrees centigrade. Now it is Jalandhar 36 degrees centigrade currently, it's hot, more humid and hot. What happens? All the ammonia will evaporate itself. That means superheated condition, we can't see the liquid NH3. But if you want to see the liquid NH3 at atmospheric pressure, mix with H2O. What is the role of H2O? it's increasing the boiling point of NH3. Let us say minus 35 degrees centigrade to whatever the temperature you want, according to the required temperature of the boiling point, you can mix it. 10%, 30%, 40, 50, 60%. That depends upon the required property temperatures. 1 minute. The required property. Yes, that is the role of adding H2O to NH3. Am I audible now?
Yes, sir.
Yes, sir.
I use some device here. Now there is no any constraints. Once you are adding H2O to NH3, there is no constraints of condenser. As per your, as usual, the ambient temperature, you may reject the NH3, but the amount of H2O, it should be weak mixture actually speaking. It may be, I think, more amount of H2O is required because our Indian climatic conditions, sink temperature, I can say 30 to 35 degrees centigrade. If I am saying, what else? Okay, that to get the 35 degrees centigrade of the saturation temperature, that's condensation temperature in case of the condenser, we need to supply more amount of water. We have to mix more amount of water. That may be more than 50%. So how much amount of water we have to mix to get the saturation temperature of 35 degrees? That means we need to study the properties of this mixer. Okay, coming to these properties of this mixer, there is one chart I am drawing here. The x-axis is the concentration. The concentration is defined as the mass of NH3 ammonia by total mass. Sorry. That's some space problem. Yeah, border. Yes, I got it. We have some border, that's why it's. So it can be expressed either molar fraction or mass fraction. X may be expressed either mass fraction, the kg by kg, or molar, kg mole by kg mole. But we need to say X is in molar base or mass base. In case, because in science mostly we are using the mass basis only. In case in the numerical problem it is given in the molar basis, we need to convert the molar into mass base. For that, that relation you may use m is equal to n into small m is equal to small n into capital M. Mass, the molecules, and molecular weight. Capital M is a molecular weight. The molecular weight of NH3, it's 17, okay, and molecular weight of water,
18.
18. MNH3, 7 approximately. MH2. See, 17 and 18 is very close. They're more friendly. And that's why one of my experiment in laboratory, what I did is, whatever the expander is designed for H2O, is designed for H2O, the same I use for NH3 also, and NH3 H2O mixer also. In fact, we have, especially we have designed this NH3 water mixer, but some extent we have some relaxation to use the equipments designed for the steam power plant. Some of the equipments used for the steam power plant that also can be used for the NH3 H2O mixer, so that we can save the money in case we are recycling the material for this type of special type of binary fuel system. That advantage also you can do. But design point of view, this is approximate use what I am saying in laboratory point of view. But design point of view, we have to design exactly based on the specific properties of this NH3 and H2O. Because these properties dynamically it is changing, change in the concentration. X is called as the concentration. Okay. Now the properties, the region of properties. X-axis is the concentration, y-axis is the temperature. Okay, if I am taking x is equal to 0 and x is equal to 1, what is meaning of x is equal to 0? This is completely NH3. X is equal to 1 means it is completely H2. Okay, if I am taking pressure, atmospheric pressure, let me take P is equal to 1 ATM, atmospheric pressure. What is the boiling point of NH3 at atmospheric pressure? Just now we discussed it's minus 35 degrees centigrade. Minus 35 degrees centigrade, approximately I am saying. And what is the boiling point of H2O, that is water at atmospheric condition?
Excuse me, sir.
Yes, yes.
So when x is equals to 0, so it should be water, I guess, because if we put the value of x is equals to 0 here in the left hand side, then it will be completely water, no NH3 will be there.
Yes, yes. Sorry, why I can- Sorry. Yes, yes. Sorry, I confused actually. So many settings here. My definition is correct. What I defined X, that is a constant, ammonia concentration. X is defined as ammonia concentration. And this is the temperature. The X is equal to 0. X is equal to 1. X is equal to 0 means it's a pure water, okay?
Yes.
It's a pure water at atmospheric pressure. What the boiling point of water H2O? What the boiling point of H2O?
100 degrees centigrade.
100 degrees. And after long time, I am using this system. But please be patient. Maybe one day it will take to get back to my practice. Okay, this is 100 degrees centigrade. At x is equal to 1, that is pure NH3, at atmospheric pressure, what is the boiling point of NH3? It's minus, okay?
Minus.
I have to keep close to x. Okay, this is a higher temperature, this is the lower temperature, and this is a fixed temperature. So what I am showing here is a fixed temperature. Fixed temperature means for the single fluid system, the saturation, that's the beginning and ending of the saturation is same. But if I am selecting the mixture of NH3 and H2O, let me take the example of x is equal to 0.5. Okay, x is equal to 0.5. The boiling, starting of the boiling is different, ending of the boiling is different. The starting, this is let me take, this is the starting of the boiling point, that is called as the bubble point temperature. Ending of the boiling is called as dew point temperature. But for the single fluid system, there is no bubble point temperature and dew point temperature. That is a constant temperature. What we discussed in Rankine cycle, the evaporation takes place at the constant temperature. After economizer, we studied the evaporator and then followed by superheater. This is a horizontal line. But in the binary fluid system, it is not the horizontal line. I am taking some bubble point temperature. I am selecting some dew point temperature. Between this bubble point temperature and dew point temperature, the phase change. This phase change means evaporator I am showing here. Evaporation takes place with variable temperature, that is starting from bubble point temperature, ending with the dew point temperature. If I am selecting keep on like this, let us say 10%, 20%, 50%, 60, 70, 80, 90, I can get series of such points. That means joining up all the locus of these bubble points and locus of the dew points, I will get a loop. Okay, this is the bubble point temperatures and top one is the dew point temperatures. Now we are able to divide the regions like super even steam, water steam properties also. We have different regions like liquid phase, liquid plus vapor, and vapor, that means superheated, etc. Similarly, here also the subcooled liquid. The liquid is two types here. The first one is subcooled. This area is completely, this is a subcooled liquid. At this point, this is also liquid, but this is a saturated liquid. Okay, bubble point temperature what we are showing, that is a saturated liquid. And dew point, because this saturation is completed, so you may call this as saturated vapor. Now between the bubble point temperature and dew point temperature, what we are calling? This is liquid plus vapor. Okay. Now above the saturated vapor, this is called as superheated vapor. Now tell me how many regions we can locate in TX diagram. TX diagram. 1,
3.
no, 5 I think so. 1, 2,
Yes, 5. 4.
3, 4, 5. So these 5 regions we are going to use in the system solutions. Well, in the system solutions, there are so many components like absorber, condenser. In case of Kalina, means even turbine also will be there. Vapor turbine also will be there. At the exit of turbine, the vapor turbine, in case of binary fluid vapor system, we don't know the condition. Let us say the exit pressure is known. We know the pressure, and we have to simulate the exit temperature. We have to iterate the temperature. And based on this condition, we have to evaluate whether that exit condition is subcooled liquid, saturated liquid, liquid plus vapor mixture, or saturated vapor, or superheated vapor. If it is a condition is given, calculations are easy. But in the reverse engineering, like prediction of or simulation of exit state of this vapor turbine, that means that's more complicated. And if it is a liquid vapor mixer, that is too complicated. Why I am saying complicated liquid plus vapor mixer? Yeah, there are so many concentrations will come. Now in liquid plus vapor, if I am drawing a vertical line, x is equal 0.5 for this entire vertical line. But if you see between the bubble point temperature and dew point temperature, the mixture concentration is same, that's 0.5 only, that's 0.5 only. But the elemental concentration, for example, I am saying this is a liquid and this is a vapor. The total concentration is 0.5. The liquid concentration only. What is the liquid concentration and what is the vapor concentration? That is different. If I am taking some temperature, let us say T is a temperature, the liquid concentration is different and vapor concentration is different. If it is x is equal to 0.5, x is equal to 0.5, what is XL? Is it more than 0.5 or less than 0.5? Hello? Are you in the live?
Yes, sir.
Is it x is equal, XL is less than 0.5 or more than 0.5?
Less than.
Less than, correct, less than, correct. More. I think Deepak is saying more. Why more? Or why less? See this vapor, the boiling point of ammonia is less than the boiling point of water. Okay, if you take the NH3 and water liquid condition and just heat it, ammonia will come out or water will come out first?
Ammonia.
Ammonia is easily it is evaporating like petrol. Easily it is evaporating like a petrol. The balanced liquid is more in H2O. The balanced liquid is more in H2O. We call this as weak solution. Why it is weak solution? As per our definition, MnH3, that is ammonia concentration. If there is no much ammonia, that's why it is weak. XL is less than, for this example I am saying, XL is less than 0.5. What about XV? XV, see, NH3 is joining here. You told just now, ammonia is first, it is evaporating. That's why more ammonia is accumulating in the vapor condition. X values keep on increasing. That's why XV is greater than 0.5. How to find this XL and XV graphically? Analytically, that is different. We have a lot of mass balance equations, energy balance equations, etc. That I will explain separately. Based on this drawing, that's TX drawing. Do you know how to plot graphically? How to plot XL and XV? That is Lever rule. Do you know Lever rule?
Yes, sir.
Okay.
Yes, sir.
For example, if this is a temperature, let me take the horizontal line. Not able to draw exactly. It is a temperature, and it is cutting bubble point temperature at one point, and it is cutting dew point temperature at one particular point. This is XL, and where it is cutting the dew point temperature, that is called as XV. So after drawing this horizontal line, you can identify this is a constant temperature. This is a constant temperature line. You can identify the XL as well as XV. Why I am saying constant temperature? The temperature of liquid, the temperature of vapor, all are same at this particular state. I am saying at this particular condition, all are same temperature. So that's why I am saying the finding the properties for the mixer is somewhat complicated compared to the subcooled liquid, or saturated liquid, saturated vapor, or superheated vapor. That is straight away you can find the properties either from the chart or from the calculations. Maybe tables. Actually, in the literature there is no tables like steam tables. We have the flexibility of solving the steam power plant either by Mollier chart, that is a chart, so graphical solution, or steam tables. But in aqua ammonia, that's NH3 H2O mixer, we only have the chart. We don't have any tables like property tables. But at the end of our book, that's this binary fluid, what I showed just now, the annexure, you can find the tables, the property tables. Okay, fine. This is a drawing. It's drawn to scale actually. What I am showing this chart, that is the temperature and the concentration chart. This is drawn to scale, and by taking the values, let us say 0.1, 0.2, 0.9, the last 0.9, 0.95 also, because there is a drastic change between 0.9 and 1. That's why 0.95 also has been selected here. Okay, we can refine the more number of points. That's fine. At what pressure it is? At 35 bar. At 35 bar, pressure is constant. Through this chart, pressure is constant. And how it is degree centigrade, how the temperature is changing. For example, at 35 degrees centigrade, the saturation temperature of water at x is equal to 0, the water is 240 degrees centigrade. If you refer the steam tables, you can find exactly the saturation properties. And at the 35 bar, the saturation temperature of NH3, pure NH3, that is it's around 70 degrees centigrade. It's around 70 degrees centigrade. Between this 240 degrees centigrade and 70 degrees centigrade, the saturation temperature is changing by changing the value of X from 0 to 1. At 0.5, 0.5, it's example I am saying, the phase change starts at 120 degrees centigrade. Approximately the phase change starts at 120 degrees centigrade, and it is ending. It's completing It's completing around 215 approximately. I'm saying 215 degrees centigrade. So this 120 degrees centigrade is the bubble point temperature, and 215 degrees centigrade is the dew point temperature. If the temperature is changing, it's maybe increase or decrease of the pressure, how this curves will change. This is one group. Let us say this is P is equal to P1, and I'm taking one more. Where P is equal. Now, based on your earlier studies, could you relate P1 and P2? P1 is greater than P2 or P2 is greater than P1?
P2 is greater.
P2 is greater than P1. So once the pressure is increasing, the loops also will increase like this. This is increasing pressure, I am saying. So what I am saying is, once the pressure is increasing, the temperature also will increase. Obviously, you know that statement. With increasing the pressure, the temperature will increase. For single fluid system, pressure and temperature is enough to solve the single fluid system. The water, you are defining the water temperature as well as water pressure. You can identify all the properties like energy, exergy, internal energy, etc. But for this binary fluid system, apart from this pressure, temperature, the additional property is the concentration, PTX. So for this binary fluid system, the concentration also we need to supply. Based on these three properties, given three properties, we can identify, for example, the pressure is fixed, concentration is, let us say, a vertical line, and this temperature will decide. If the temperature is below the saturation, below the bubble point temperature, you may commit that is subcooled liquid. If the temperature is given, temperature is equal to the bubble point temperature at Px, you can conclude that is the saturated liquid state. If the given temperature is between the bubble point temperature and dew point temperature, you can conclude, decide that is a liquid vapor mixture. And if this temperature is equal to the dew point temperature, you may say that state is saturated vapor condition. If this temperature is, if this given temperature is greater than dew point temperature, what is your conclusion? You will say this is the superheated vapor. So that's why temperature plays an important role to decide the state. Out of 5 states, just now what we had a discussion, subcooled to superheated vapor, the temperature will say you are here, you are here. Okay. Are you clear in today's class? Tomorrow I will continue extending these properties. Today, sorry, this is after I think 1 semester I am using this distill tab. That's why some practice, lack of practice, I am not able to draw. I think 1 or 2 classes I will get practice. Is it clear what I am writing? The thickness of line, or it's not clear? A small letter or something.
Yes, it's clear.
Clear, sir.
Yes, okay. For me, it will take 1 day. It will take time. I will practice because sometimes it is fitting and border. Once I am moving away from the border, it is coming out. Okay, that's not the issue. You should handle this.
Sir,
Yes. Okay.
sir, on what basis we decided zone 1 and zone 2?
That's just now I told, based on temperature. Based on temperature. Yes. Based on this, are you able to see the screen?
Yes, sir.
This is pressure is fixed here, 35, and I am saying your state is, let me take arbitrary, 145 degrees centigrade. Pressure is 35 bar. Temperature is 145 degrees centigrade. Concentration is 0.5. Now could you say what the state? Condition I am saying, region. There are 5 regions here. At 35 bar, 145 degrees centigrade and 0.5 concentration. How that mixture looks? Is it liquid or vapor or mixture? How you can say? Draw a vertical line at 0.5. Draw a vertical line at 0.5. And 145 is, where is 145? It is above 120 and below 220 or 215. Obviously, you can say your answer is liquid plus vapor. Got it?
Yes, sir.
If the temperature is below 120, your answer is subcooled liquid. But if you are changing the concentration, again your answer will change. That's why it's dynamic. The binary fluids properties are too dynamic. Have you got the answer?
Yes, sir.
Okay, any else? And I am not using any figures from the textbook. All what I am showing, all the figures are my own drawings from the published book. And also I use the MATLAB to draw all the properties, process, and the systems, including polychaptation. Okay. Now I will take the attendance. If you have any questions, you may ask me. Number 2, Akshay.
Yes, sir.
Akshay Sangra. Amnish.
Right, sir.
Amnish, are you able to see the screen?
No, sir.
Okay. Amnish.
Brilliant, sir.
4.
Yes, sir. Brilliant.
5, Manoj.
Present, sir.
Manoj, you came for today's first class?
Yes, sir. Yes, sir.
Deepak,
Yes, sir.
Zahid, Zahid, Priya Das,
Yes, sir.
Dipesh,
Good evening, sir.
Swapnil,
Present, sir.
Vaibhav.
Present, sir.
Vaibhav, you have one absent, am I correct?
Oh, yes, sir. Actually, I was wrong.
Yuvraj,
Yes, sir. Present, sir.
Yuvraj, yesterday,
Yes, sir. Yes, sir.
when you are coming, Jalandhar,
Sir, actually, I don't know, sir.
are you booked the
Still, I don't know, sir.
You have to book the ticket early.
Yes, sir.
You don't know. Okay, fine. Next one to Mishra.
Yes, sir.
Mishra.
Present, sir.
Okay, fine. I think all today except Jahid, all came.